Hello, everyone. My name is Aravind Sankaran. I'm a PhD student at RWTH Aachen University, Germany. I'm here to talk about making intelligent performance measurements with reinforcement learning. We consider scientific codes that are a sequence of mathematical tasks. Each task is some high-level math expression, such as a matrix chain or a solution to a least square problem, etc. Each task can be implemented using many possible algorithms. For instance, here I show two different parenthesization for a matrix chain of length 4. Both the algorithms are mathematically equivalent, but the number of flops can differ, so the performance can also be different. The performance also changes based on the choice of BLIS calls. For example, if A and B are symmetric, calling sim instead of gem reduces the number of flops by half. It is also possible to come up with different programs by identifying calls that can be executed concurrently. But parallelization does not always reduce the execution time because of communication overheads. So we do not always have a clear roadmap in selecting the best algorithm. So each mathematical task in the code can have many different algorithms with varying performance. Therefore, when considering all the permutations, the whole scientific code can have a large number of possible algorithms. Sometimes the search space can be so large that we cannot execute all the algorithms. So we assume that we are given a time budget. The budget can be smaller than 1 hour or as long as a day or a week. We can choose it, but our goal is to make as many intelligent measurements as possible. We aim to solve this problem with reinforcement learning by training an AI agent. From the large search space, the agent samples a small set of algorithms, measures them, and softly clusters them into performance classes. In our previous work, we introduced a methodology to rank the algorithms into clusters. The relative score indicates the possibility of an algorithm to belong to a specific cluster. For instance, the red algorithm here has 30% chance of belonging to the best cluster C1 and 70% chance of belonging to the second best cluster. In our work, we showed that relative scores are reliable even when the number of performance measurements made are very less. The relative scores help the AI agent to discriminate the good algorithm from the bad algorithm. An algorithm in the top cluster gets a better reward. The agent then tries to pick an algorithm such that its reward is maximized. Once picked, the agent then measures the algorithm to verify against the true reward. In this case, the reward is not too good. The agent learns from this and then tries to pick a better algorithm next time. The learning process is done via a neural network. The neural network maps the cluster table with the features of the algorithm, such as sequence of flops, choice of BLIS calls, and then selects the algorithm that is expected to give a higher reward. Agent then recomputes the cluster and the reward. The reward is expected to get better through the iteration, and the process is repeated until the time budget runs out. For further information about this methodology, have a look at our long video. See you at the Q&A session. Thank you.